Why can't we solve these problems? We know what they are. Something always seems to stop us. Why? I remember March the 15th, 2000. The B-15 iceberg broke off the Ross Ice Shelf. In the newspaper it said it was all part of a normal process. A little bit further on in the article, it said a loss that would normally take the ice shelf 50 to 100 years to replace. That same word, normal, had two different, almost opposite meanings. If we walk into the B-15 iceberg when we leave here today, we're going to bump into something 1,000 feet tall, 76 miles long, 17 miles wide, and it's going to weigh 2 gigatons. I'm sorry, there's nothing normal about this. And yet I think it's this perspective of us as humans to look at our world through the lens of normal is one of the forces that stops us developing real solutions. Only 90 days after this, arguably the greatest discovery of the last century occurred. It was the sequencing, for the first time, of the human genome. This is the code that's in every single one of our 50 trillion cells that makes us who we are and what we are. And if we just take one cell's worth of this code and unwind it, it's a meter long, 2 nanometers thick. 2 nanometers is 20 atoms in thickness. And I wondered, what if the answer to some of our biggest problems could be found in the smallest of places, where the difference between what is valuable and what is worthless is merely the addition or subtraction of a few atoms? And what if we could get exquisite control over the essence of energy, the electron? So I started to go around the world finding the best and brightest scientists I could at universities, whose collective discoveries have the chance to take us there, and we formed a company to build on their extraordinary ideas. 6.5 years later, 180 researchers, they have some amazing developments in the lab. I'm going to show you 3 of those today, such that we can stop burning up our planet. And instead, we can generate all the energy we need right where we are, cleanly, safely, and cheaply. Think of the space that we spend most of our time. Tremendous amount of energy is coming at us from the sun. We like the light that comes into the room, but in the middle of summer, all that heat is coming into the room that we're trying to keep cool. In winter, exactly the opposite is happening. We're trying to heat up the space that we're in, and all that is trying to get out through the window. Wouldn't it be really great if the window could flick back the heat into the room if we needed it, or flick it away before it came in? One of the materials that can do this is a remarkable material, carbon, that has changed its form in this incredibly beautiful reaction, where graphite is blasted by a vapor, and when the vaporized carbon condenses, it condenses back into a different form. Chicken wire rolled up. But this chicken wire carbon, called a carbon nanotube, is 100,000 times smaller than the widths of one of your hairs. It's 1,000 times more conductive than copper. How is that possible? One of the things about working at the nanoscale is things look and act very differently. You think of carbon as black. Carbon at the nanoscale is actually transparent and flexible. And when it's in this form, if I combine it with a polymer and affix it to your window, When it's in its colored state, it will reflect away all heat and light, and when it's in its bleached state, it will let all the light and heat through, and any combination in between. To change its state, by the way, takes 2 volts for a millisecond pulse. And once you've changed its state, it stays there until you change its state again. As we were working on this incredible discovery at University of Florida, we were told to go down the corridor to visit another scientist. And he was working on a pretty incredible thing. Imagine if we didn't have to rely on artificial lighting to get round at night. We'd have to see at night, right? This lets you do it. It's a nanomaterial, 2 nanomaterials, a detector and an imager. The total width of it is 600 times smaller than the width of a decimal place.